my PhD thesis was some of the foundation for a technology which became involved in a startup company called Transitive Technologies, and one of their most successful products was Rosetta. And it's good to see lots of MacBooks around here and so on, because they'll have Rosetta on them and so on. I did a lot of work on a metacircular, semi-famous virtual machine. I have a book chapter in a book by O'Reilly. The book is called Beautiful Architectures, and it's been translated into Russian, Japanese, and Chinese. And I only have the Chinese version in the US for obscure reasons. But it's nice to have been translated. I'm a software engineer for Azul Systems. I mean, I do more than just coding. I also, engage my brain. And it's something we're encouraged to do at Azul. We're not just code monkeys and so on. So, so my old research group boss was Steve Ferber, and I'll probably keep mentioning about how great Manchester is. It's something that I do. Manchester in the UK, that is. I hear there are other ones. And Steve Ferber is a Mancunian, and he was one of the co-developers of the ARM processor. And what people used to say at the University of Manchester was that Steve is a great professor, but whenever he teaches a course, he starts with transistors and then builds up. And so I'm going to kind of do something a bit similar tonight, and kind of start low level with the JVM and build upwards. And if people have problems with it, raise your hand, and I'll hopefully be able to answer your questions and concerns and so on. It's a fairly new slide deck, so I expect people to have problems and issues with it and so on. And I've got a whiteboard and whiteboard markers, so that's good. What I'm going to do is kind of introduce some of the underlying technologies for the JVM, how it achieves portability, and then kind of go into some of the more challenging and novel aspects of the JVM and how kind of performance is achieved in those areas. And then I'm going to start talking about what we're doing at Azul Systems with the Zing virtual machine, which is kind of the latest generation Azul solution. Okay, so a JVM described in a simple sentence, so reading slides. A software module that provides the same execution environment to all Java applications and takes care of translation to the underlying layers with regards to the execution of instructions and resource management. That's a big sentence. Let's look at a picture. Okay. We've got some code. We can take the same piece of code and we can run it on 2 different hardware architectures and 2 different operating systems. And the JVM is the thing which is doing the mapping between these things. And the JVM is doing a whole lot of stuff. It's mapping, the Java bytecodes down to the hardware architecture, and it's also dealing with things like, giving you a consistent threading model and things like that. I haven't done any slides on threading models, but if people are interested, I can talk about threading models. Okay. So, starting at kind of the beginning, the interpreter. So we have Java bytecodes. They're wrapped up in a Java class file, and when you write your Java program, you'll compile it into a .class file. I'm assuming that's familiar to people in this audience because of who you are and so on. But we need to kind of bridge this gap, and the simplest way to do it is with an interpreter. So, and kind of, although I work on metacircular JVMs and so on which don't have interpreters, in general, in production VMs, you still need an interpreter because you still end up with large methods that are run infrequently, and it's not really worth spending the energy doing the compilation. And a good example of that is in servlets. Okay, so let's kind of look at a silly interpreter, thing that I've written up here. So I have an infinite loop, we're running forever, and we're fetching bytecodes from a bytecode stream, which is, a class file we've loaded into memory. I'm going to read a byte out of the bytecode stream and advance the program counter at the same time. And then I'm going to do some switch statements on the bytecode. So I'm going to decode what the bytecode's meaning is and kind of dispatch it and work out what's the operation I want to perform. And then I'm going to perform some operation. So here are 3 example bytecodes. I've chosen some easy ones because that makes it easy for me. And what these bytecodes are doing is, iconst1 is just going to put a value of 1 onto what's known as the expression stack inside the interpreter. An iload of 0 will take a local variable and put that onto the stack. And iadd will pop 2 things from the stack, add them together and push the result onto the stack. And this is pretty much how the JVM is defined. If you look in the virtual machine specification, you'll see that they'll have, this is what a bytecode is, this is what the expression stack looks like before, this is what it looks like afterwards, and here's the transformation from one to the other. And, okay. So, this isn't very efficient. We have a lot of branching going on. We've got to decode each operation. And we've got to manipulate the local variables in the stack. We can do better. You can do better inside interpreters. You can do things like threaded interpretation. So with threaded interpretation, here we have a single switch statement which is going to branch to one of these bytecodes. With a threaded interpreter, instead of having this break which is going to go down here and conceptually we're going to go back down to there, with a threaded interpreter, you basically branch to the next bytecode, kind of where the break statement is there. And GCC will actually do this as a compiler optimization and so on. So a lot of these things can be done for you. We're always going to be kind of accessing memory for manipulating our stack or local variables. So if we want to have an efficient interpreter, and we've got access to kind of like the machine, the low levels of the machine, we can start putting these values into registers in the machine, and that means we can avoid accessing memory. One of the kind of like more advanced techniques is to kind of pre-decode the bytecodes and just realize that, bytecodes are just going to arbitrary addresses, so you can just create a list of those addresses. But people don't tend to do that because you might as well compile when you're getting into that level of complexity. And then there are other tricks like optimizing the dispatch, so it's just a arithmetic operation, which is one of the tricks done in the Dalvik VM. Okay, so interpreters, that's it, done. Any questions? No, good. So interpreters are intentionally simple, but their performance isn't that great. So we want to do just-in-time compilation. And just-in-time is one of these terms which I believe the Japanese actually stole from America, from a grocery chain. But there's a whole origin to just-in-time that I'm not familiar with. But just-in-time inside a virtual machine means that we have some code, we're executing it frequently. Let's compile it so that it runs faster. We don't compile everything, we just focus on running the hot parts of the code. So, you get names like hotspot, indicative of the fact that you're just concentrating on compiling the hot regions of code. So, I'm going to talk about every single bit of a compiler. Isn't that scary? It shouldn't be. And hopefully, I'll do a good enough an explanation that you can kind of follow how a VM compiler works. And so stop me when you're failing to understand. It really shouldn't be that hard. So the first thing we want to do is we want to turn the bytecodes into some kind of graph representation. Now the reason we're going to do this is because we want to eliminate the overhead of having this stack and so on. And I'm going to show you what the graph representation looks like, and I'm actually going to use examples taken from hotspots, so it's scary, but not really. The next thing is we've got this graph of our instructions connected together. What we then want to do is we want to linearize the graph, because instructions inside a computer are addresses and they're sequential in memory. So you've got to linearize that graph somehow. And so I'm going to talk about how that's done. At that stage, you have this infinite pool of virtual registers. And then the next thing that needs to happen is you need to map that infinite virtual pool of registers into some finite resource within the processor, some finite number of registers. And, mapping infinite into finite doesn't work. So what happens when it doesn't work? Well, you go and use the stack in memory. then once you've got instruction nodes and registers allocated to them, then you can actually do some code generation. So let's start off with a very simple Java program. So this is Fibonacci. So Fibonacci is just kind of a simple recursive routine for computing the Fibonacci sequence. It's written recursively. There's no clever optimizations in this. I wanted it to be a simple example and to fit onto slides and so on. But it's a kind of a classic example at the same time. So let's go from the Java to the bytecode. Now, are people comfortable with bytecode in degrees? So what we can see in the bytecode is that we're going to access local variables and push constants onto the stack, as I mentioned earlier. And I can kind of work through this on the whiteboard if it's useful to. What we can see from the definition of the method is that it takes an integer as a parameter. In the JVM, the first argument is in the first local variable. So this iLoad of 0 is actually taking the integer argument and putting it onto the stack. Then we're going to push onto the stack the value of 1. And then we're going to do a greater than comparison. And if it is greater than, then we're going to go to location 7. So if we flip back to our original code, this less than equals than sign has been kind of flipped around from being less than equals to be greater than. And the bytecode immediately following this compare and branch is going to put a 1 on the expression stack and return in the case that it's less than or equal to 1. So is that kind of clear? Kind of what's going on with that flow and so on. So, good. I'm not scaring people yet. So then we get down to kind of bytecode 7. It's going to load the incoming arguments again, the value of 1, subtract it, and then it's going to recursively call the Fibonacci method. So this directly corresponds to this call here. We're doing n-1 and we're recursively calling Fibonacci. So the result of that will get left on the expression stack. And then here we load the incoming arguments again, we load the value 2, we subtract them, and we do another recursive call. Finally, we add the two values together, and then we return. So hopefully people can see that there's been a kind of a syntax-directed translation of the Java code into the bytecode. There's not really been any smarts or cleverness going on. It's a fairly literal translation from one to the other. So, people happy? You're wondering where I'm going with this. Okay, we're going down, of course. Okay, so going back a few stages, I was saying that the next thing that's going to happen is that we're going to build up a graph of nodes. And the client, the C1 compiler inside Hotspot. And what happens is you have basic blocks. So when you have a block structured code like this, you can imagine that this return 1 is one block and this other return is another block of code and so on. So the term basic block can mean different things at kind of high level and low level within the compiler. Looking at what we've got here, and here are the command line arguments to get you this printout from this very method that I was showing you a few seconds ago. You can't get this dump out to a regular JVM. If you use the Java _G, then that's the debug version of the JVM, and you can see what's going on inside the VM. You can see the VM internals yourself, and you can go and what horrible code have you generated for my method, and so on, if you really care. So the first basic block we have is just the entry basic block. Here we have two graph nodes. We have a graph node which is a constant 1, and we have another graph node which is a comparison between two other graph nodes and a branch to one of the two basic blocks based on those things. And we can see here it says I3. So where is I3? I3 isn't defined. I3 is actually the incoming argument to the method, and I4 is the constant 1. Okay, So we then have basic block number 1, which has got this I6, which is again is the constant 1, and I7. And I7 is just an I-return graph node with an I6. So you've got this graph of blocks, and they've got a list, they've got instructions, and the instructions are kind of defined in terms of things coming into them. So they kind of internally form and I've chosen an example which doesn't really show one of the more complicated operations. This compiler intermediate form is known as static single assignment, and so there's an issue with static single assignment. What single assignment gives you is it gives you this property that things are only written to once. So here we're defining a value to I6. Here we're defining a value to I7. We've only defined these values once. And what this gives you as a property inside a compiler is that you only have true dependence. So if you're kind of a hardware guy, then it's kind of a read after write dependence. So something's written and then you read it. And that's the only kind of dependence you're allowed. You're not allowed write after write, because that would mean that you're writing to it twice. It wouldn't be single assignment. And you're not allowed anti-dependence, which is where you have a write after a read. And so how do you deal with loops and things like that where you do get that property? You have a special instruction node called a fee, and a fee instruction takes inputs which are other instructions, but the choice of which instruction you use is based on where the graph is coming from. And it sounds complicated, and it is. There are PLDI papers on how constructing it is not too bad. Deconstructing it is kind of a more tricky situation. So anyway, we've got this graph, and we can see here, this is kind of like the more complicated bit from the example, where we're taking this input argument again, we're subtracting 1 from it, we're doing the recursive call. We're taking the input argument again, we're subtracting 2 from it, and we're doing the recursive call. We're adding the two values together, and then we're returning back to the caller. So hopefully you can see how we've gone from the Java source code down to this graph of instruction nodes, kind of step by step. Okay, so we're going to go even further down. It was transistor. I'm going down to the transistors from my source example. So the JVM option for this is print IR with LIR. So IR means intermediate representation, and inside the client compiler, intermediate representation means the graph, and the LIR means this kind of low-level intermediate representation, which is the representation when things have been made into a linear list of instructions. We can see what's going on is that my graph node here immediately afterwards has these LAR instructions associated with it. So what's happening here is it reads left to right. So we're moving the value in RDI into this virtual register from my infinite pool of virtual registers. It's fantastic. I've got this infinite pool of virtual registers. I don't need to worry about memory. I'm moving RDI into R36. And RDI is actually, from the calling convention of the VM, is the incoming argument register. And this is the Zing virtual machine I'm taking this example from. So you may see different things if you're using a different VM. There's some stuff here to do with save points. I'm going to skip over that. It's more to do with garbage collection. And I've got stuff at the end to kind of talk about what goes on with garbage collection. And here we have a branch which says always branch to block number 0. So block number 0 is here, and it's going to do the comparison between R36, which is what was defined up here, and the value 1. And the value 1 has gone from being in its own individual graph node and just being folded into this instruction, which is one of the things that happens with the LIR construction in the client compiler. So we're doing a comparison between this virtual register number 36 and the constant 1. We're going to branch if it's greater than to block number 2, which is over there. Otherwise, we're going to fall through. Then if we fall through, we're into our case where we're going to return 1. we go and put the value of 1 into RAX, which is the result register on Intel processors commonly. And then we're just going to do the return, and the return kind of implicitly uses the RAX register, but it doesn't actually in the Intel architecture. But not to worry about these things. So over here we have our graph node for doing the subtraction, I3 minus I4. That turns into a move of the value of R36 into R37. So over here we copied the input argument into R36. Over here we're copying the input argument into R37 and creating redundant copies. When we're doing this kind of construction, we don't worry about having lots of copies because the register allocator's job is actually to remove copies. So a good register allocator will eliminate all of the copies. So we move the value into R37, and then we're going to subtract from R37 the value 1 and put the result into R37. So you might observe here that we could have just subtracted 1 and R36 and put the result into R37. Intel instructions only have 2 operands, and so this is something that goes on inside the client compiler to try and facilitate easy mapping from the compiler intermediate form to the Intel instructions. Is just to make 2 of the arguments the same. If you're doing this on a RISC architecture, which tends to have three address instructions, then this actually doesn't happen by the client compiler and so on. So there are some differences in terms of the compiler intermediate form, depending on which architecture you're targeting. So we've done the subtracts of 1, then we're doing the recursive call. Here we're going to do the subtract of 2, and we've got the subtract with 2. We've made another copy of the incoming argument into R39, a recursive call, and then finally we've got our add and our return down there. So we've gone down a layer. We've gone from having a graph and we've gone to a linearized list of instructions, but we can't yet run these instructions because they're using registers from an infinite pool, and processors don't have infinite pools of registers. And so the next thing we must do is register allocator. And at the bottom again is the kind of the Java G option, which will show you what's going on inside the compiler when this next thing happens. And on Intel processors, the register naming convention is somewhat wacky, so try not to think too much about it. But hopefully what you can see is that I've got rid of the graph nodes from the IR. So here we just have the LIR instructions, which are in a list. Starting at 0, they go through to 52, so they're in a list. And now, instead of mentioning things like R36, they mention specific registers. So we're going to move RDI into RBX, and here we're going to compare RBX with the value of 1. And these directly correspond to the things we had before, except instead of having an infinite pool of virtual registers, we now have specific ones. And the other thing that's gone on is that we've lost moves. So the moves have been eliminated by the register allocator, because the register allocator is always trying to make sure that the source of a move and the destination of a move are the same thing, and then the move is doing no work at all, so it just eliminates the instruction. So finally, we get the Intel machine code for that. And there's some boilerplate in here. So there's some boilerplate for kind of saving registers. There's some boilerplate for restoring the registers which were saved. But you can see that I've got to compare with EBX and the value of 1. And here we had a compare with RBX and the value of 1. The E and the R's are somewhat arbitrary. The R's mean 64-bit versions of the registers. It's an integer, so it's really a 32-bit version of the register. But for simplicity inside the compiler, we just assume it's going to be a 64-bit. Down here, we have the calls, which are going to be the recursive calls. We have a decrement, which is a subtract of 1. We have a subtract of 2. We have, again, the recursive call. We have at the end the add, which is going to add these values together, and we're going to make sure that EAX holds the result at the end, and then we're going to restore the registers which need to be preserved, and do the return. So that wasn't painful.
Could you quickly explain what C?
It's a complicated thing. So the VM allocates memory all the time. Java has this brilliant property of having memory safety. You never free up the memory. Memory safety is a good thing, gets rid of whole classes of bugs and so on. It means people can develop Java code very quickly, and it's a whole advantage of using Java. The problem with allocating memory all the time is every once in a while you want to stop the application from changing memory. And what a save point is, it's a way of the VM to request that all of the application threads stop running to let the garbage collector threads to run. So you can see here that what's happening is there's a comparison to say, has some flag been set which says I need to stop running? And if so, go to the place where I stop running and let the garbage collector run. Okay? And I'll mention something about stop the world garbage collectors and concurrent garbage collectors. And one of the take-homes from this talk is that concurrent garbage collectors are the be-all and end-all, and you want to pay big money for them. So there's a little bit of extra code which wasn't mentioned in anything in the kind of the push down, which was to do with exception handling. So in Java methods, you might call through to something. This code does method calls, and those things might throw exceptions. And what this code does is it just goes, in that case, you know, just do it doesn't quite say it, but what this will achieve is just returning to the thing which called it and say, I don't handle this exception. So by default, every bit of generated code will have something which says, if I don't handle this exception, make sure that I return to the caller and make sure that they try and handle the exception. And then there's a little bit at the end here to do with deoptimization. And deoptimization is something that I'll kind of pick up on a bit later. So this slide deck was done by someone other than me, and they thought that dead code elimination was a great compiler optimization. And I think dead code elimination means that you're writing bad code. Because if there's that much dead code, it shouldn't be. No, it's not quite true. Especially if you're writing metacircular runtimes and things like that. You have big bits of your code base which aren't necessary all of the time. They might just be there for debugging and things like that, in which case you can eliminate them. You can reduce the size of the generated code. Prevents irrelevant operations to occupy time in the CPU. Yeah, not my statement. But basically, having code which isn't useful to the running of the program, get rid of it. And so guess what? The compilers do that. Okay, now method inlining. So, you know, the first time I was in California was for JVM 01, so I am older than I look. And one of the take-homes from JVM 01 was that when it comes to optimizing Java programs, what's the main trick that the JVM does is it inlines and then, you know, if it still isn't going fast enough, it inlines again. You know, just inline, inline, inline. It's one of the key tricks. And what inlining does is it takes a method. So in this case, we've got this days left method, and rather than calling it, it inlines the code of the method body into the call site here. So it's getting rid of the call into the method. And you saw that, you know, from the deep dive into what the compiler was producing, there's a certain amount of boilerplate to do with entering a method and returning from a method. So the inlining gets rid of that, but it also enables other optimizations. So if you see in this example, it's passing through the value of 0. And here, if x equals 0, we're going to return 0. And guess what? In that situation, this else statement is dead code. So inlining enables you to do constant propagation. So it's propagating constants and then eliminating code which then turns out to be dead because it was unreachable, and so on. So this is going a bit more depth with what the previous example looks like when you've taken the method body and replicated it all of the times which were necessary. and yet more. So constant propagation. Okay, lovely. Redundancy removal. So this slide was written by a marketing person. I would call it common subexpression elimination. But anyway, it's if you have two things, two statements which are doing the same thing. So if I have, y equals x plus 1 and z equals x plus 1, then why do I do the work of computing x plus 1 twice? I can common up the work and just have x plus 1 once. And I can say z equals y. And it sounds like it should be a very complicated optimization. I assure you it isn't. Basically, you work out a way of putting all of the instructions into a hash table. And if you see that you get a hit in the hash table, that means you've seen this instruction before. And then you go, waha, I don't need to do the work. I can just reuse the result of that instruction. And that kind of falls out from static single assignment form, which is why compiler people like static single assignment form, and so on. Okay, so the first two examples were from marketing, and then here's one that I like. Low-level tree rewriting. So what have I got? I've got a class, and my class has got a field in it, and I've got a very simple method. My method is just going to increment the field. So is that over anyone's head? Good. So what do we get when we turn this into bytecode? We get a get field instruction, which is going to read the field and push it onto the expression stack. We're going to generate the constant 1, and we're going to add the two top of the stack values together. So that's going to do the plus plus operation. And then we're going to do a put field to write the result back. So whilst in the Java code, oh, I've missed a semicolon, so shoot me. But so whilst in the Java code, this is a single expression. It's turned into many bytecodes, as you can see from this example. I did actually compile this, but I obviously didn't copy the code I compiled into this. So, when I did the kind of the deep dive from the source code down to the instructions we generate, what we'd end up with in that case is, the get field would turn into a load of the field into some register. I'm calling it R1. I'm going to move the value of 1 into R2. I'm going to add the two values together, and then I'm going to store the result back into memory. And hopefully, you're now feeling somewhat comfortable with how that code could actually be generated by the VM. To the root when computing the linear form. So when you tend to, it depends where you do this. In the metacircular VMs, I've already linearized the code when I'm doing the tree rewriting. If I'm doing this in a compiler like the server compiler in Hotspot, then that has a tree. The whole thing is in a graph, and you can look at regions of a graph as if they're trees. Is it true that you work from the leaves upwards? I think the answer is yes. So, yeah, hope that answers it. Yes. Okay, so what I want to kind of look at as a compiler optimization is tree rewriting. And so what I can observe is that this part of my tree is just adding a constant 1. In which case, previously, I was moving the constant 1 into a register. What I can do is I can just directly add the constant 1 onto the register, assuming that I've got a machine which can add constants to registers, which most do. Okay, so that's nice. I've saved an instruction. On x86, you can do better than that. You can just directly add 1 to a memory location. So what I want to do in that situation is to recognize this whole tree and then realize I can do an add with memory. Okay? Ooh, compiler magic. How does it happen? So,
does that happen
So a regular add with memory will actually, in the x86 hardware, will become a load, add of 1, and then a store. There's a variant of that on x86 where you can put a lock prefix on it, and that will make it atomic. Yes? Entirely. So when we went from the Java bytecode to the graph of instruction nodes, then we eliminated the notion of local variables and stack. What we had was we had instructions which generated a value, and then we had edges which put those values into other instructions. So, I mean, in a way, this code doesn't have anything to do with the stack because it's kind of happening way down in the compiler at the point where I've got these LIR instructions which are saying, you know, do a load, do a store, and I'm recognizing I can fold them together. So, yep, nothing there. Okay, so, you know, this looks like it should be amazing compiler magic, and you know you need a PhD or something to try and understand this amazing compiler magic. Bullshit. What happens is it's an algorithm which is about as complicated as diff or something like that. What the algorithm does is it tries to do every possible covering of a tree until it realizes that it doesn't work. And so what we start off with is we put a covering and we go, okay, here, you know, I can do a get field and I can see that that's got a certain cost if I generate the result into a register. And these cost functions are actually just arbitrary numbers. We can generate this constant into a register and that'll have a cost. We can realize that we can fold these two operations together and that'll have a cost. So what we do is we label the tree. And when we've labeled the tree, we can then do a traversal which just selects the least cost traversal of the tree.
How is a brute force looks like that acceptable?
That acceptable when you're doing this at runtime. Is fair assumption? Yeah, approximation. So instruction selection in hotspot only happens in the server compiler. In the client compiler, it's kind of, other than recognizing that it's got a constant 1 going into the add instruction, it doesn't do anything else. And you use the client compiler for most warm code. You only start using the server compiler for extremely hot code. So whilst your compile of the compile of the bytecode may take a little bit longer, you're going to recoup the cost because this code is very hot. So there's a kind of a cost-benefit analysis that the VM has to do to determine whether it should expend energy doing compilation and so on. Okay, high-level tree rewriting, new stuff. This stuff's good fun. And yes, JVMs actually do this. Unfortunately, it's not as well structured as it should be. The previous optimization gets captured in what gets called as the architecture definition for a CPU platform for hotspots. This kind of stuff is less formally defined and tends to be kind of hacked into the VM, but it's good stuff, so we should talk about it. And hopefully you'll appreciate why it's good stuff. But I might be kind of overshooting, but we'll see. So can people understand this code? I've got 3 strings, A, B, and C, A, B, C. I could have made the method static. And what I'm going to do is I'm going to concatenate the 3 strings together and just return it as a result. Okay, so again, not fantastically complicated. And again, Java-C, the Java to class file compiler has done some magic for us. It's going to actually use a string builder. And the concatenation operations are going to turn into string builder append operations. So we're going to create a new string builder with our first string A. We're going to concatenate B onto it. Then we're going to concatenate C. And then we're going to turn the whole thing into a string. And although the original code mentioned nothing about string builders, the new code mentions string builders. And this is kind of, there's nothing the JVM can do about this. The JVM will see the string builders, and in Java 1.4 they'll string buffers, and there's a whole slew of literature you can go and read about that. But basically, you've got this code, and I'm going to say it's not very good. So that's a very good point. So the question was, why not look at the lengths of the strings A, B, and C, and add the length of those 3 strings together, and then when you create the string builder, create it with that length, and then you can avoid this inefficiency that if the original string builder is too small, you can then end up growing it in the append operation. And then they've got this extra append operation, which is again going to grow it. So I'm going to say that that's what we're going to do. However, what I need a new constructor to string builder, which can take multiple strings and append them together. Okay? Now, people are probably going to jump to the Java API documentation and go, well, no such method exists. There are methods that exist on these things which you don't know about. How does that actually achieved? String buffer and string builder have a common parent class. I think it's called abstract string builder. And abstract string builder has these methods on them. But abstract string builder is package protected. And so no one outside of Java Lang can see it. Java Lang, Java Util? Java Lang. And so what actually happens is this new string builder is actually a method on this abstract string builder, which takes these 3 things. And so hopefully you can see that, earlier I was talking about doing efficient mapping of certain instructions to Intel instructions. Here I'm talking about mapping several kind of high-level JVM operations into kind of a more efficient JVM operation. And this can avoid kind of memory allocation and other things like that. So there's lots more optimizations, and I got bored of writing slides. And so on. So you can pretty much do any optimization you want. And the question which will get thrown back to me is, well, it's at runtime, you can't do this. And basically, there's a kind of a law of diminishing returns. The more optimization you do, the less performance you get. You should kind of focus your attention. And then there's this very popular 80-20 rule or 90-10 rule, depending on who you talk to, that you spend 80% of your execution time and 20% of your code. If you've got code like Eclipse, then that's a lot of code, but it's still kind of true that you spend most of your time in certain hot pieces of code. So the JVM will do complicated optimizations like loop unswitching, loop unrolling, loop invariant code motion. I can tell you about those, but just believe me, they're all good stuff. You like them, they make your code run faster. There's data flow analysis. Data flow analysis is really nice. What it does is it lets the VM propagate information through the graph that we were talking about earlier. So one of the things that you have in Java is you have the ability for runtime exceptions to occur in lots of different places. So one of the runtime exceptions which can occur is a null pointer exception. However, I can guarantee that the this pointer is never null. And so what I can do is I can propagate that information through the graph, and anywhere I see, compare with null of a this pointer, then I can get rid of that code. It's dead code, and so on. And what data flow analysis can do is it can do, more impressive things than that. It can say this integer is within these ranges, and that's never going to be outside the range of an array length. And so it can eliminate bounds checks and things like that. So believe me, the VM's very smart. There's lots of people working on it. We're doing good stuff. There's vectorization, I've spelled it correctly, good, where you're trying to take advantage of the SIMD multimedia instructions which are on modern processors. Modern, you've been able to buy them for like 15 years. So, code layout. Code layout is a big win. It's just getting the hottest bits of code all in a straight line of code and making the branches go to the less common bits of code. If you have profiling, you can do this. The JVM is a hot running system. It can profile all the time, and so it can do very good code layout. This is one of the main kind of like advantages of a JVM over a static compilation route like C and C++. Escape analysis, deliberately put there because it's a good optimization. So it's very common in Java to have a collection and then to say, I want an iterator over that collection. And that iterator will commonly have one field inside it called next. And that next is just going to go along your linked list, or is going to go down your array list, or whatever it's going to do. And if you're just using that iterator inside a single method and you've inlined all the code, then what you'd like to do is take that next field and place it in a register. You don't want to do any memory allocation for it, and so on and so forth. So what escape analysis does is it looks for allocations of memory, and it tries to see if they can in some way escape. So an escape is where you take the freshly allocated iterator and you write it to a field, or you do or you return it, or something like that. If that's outside of the code which has been inlined, then you'll disable the escape analysis optimization, and your next field won't get put into a register, and you will actually allocate some heap. So an escape analysis is very nice and very good, and kind of it's much more common inside the VM than people give it credit for. Don't avoid iterators because you think they're allocating memory. They shouldn't in a decent VM. You know, Dalvik, you know, doesn't do escape analysis, but anyway. So the JVM has a bunch of challenges. So being object-oriented is a challenge. You have virtual method dispatch, and it's certainly true in kind of older processes that virtual method dispatch had a penalty compared to kind of just being able to call a specific target method. And if you look at what Java did compared to C++, it very deliberately made everything virtual by default. Every method is virtual. You can override it, unless the class is declared final or the method is declared final, and so on and so forth. So Java is encouraging you to do object-oriented code writing. Unlike C++, which makes you type the word virtual if you actually want to make object-oriented code. So it's making you pay a penalty by making you type a word. In C++, because it's being statically compiled, what they must do for the method dispatch is they must create a dispatch table where when you do the virtual method dispatch, you have to load a value out of the table and then call through to that. So you've got a load followed by a call. And normally it's much worse than this, and girls there in the audience can scream at me and say it's far, far worse. What happens inside the JVM is for example, if you have an interface, that you only have a single class implementing that interface. So if that's the case, then why don't I just call the method that belongs to that single class? The interface doesn't have any method declaration. I know there's a single implementing class. There's only one place I can go to. Why do I need to look it up in a table? There's no need. So I can make an optimistic optimization which says I'm just going to go to this one place. But inside the VM, I can remember that I made that observation. And if that ever proves not to be true, I have to do this thing called deoptimization, which is basically I throw away the generated code, I recompile it if it becomes hot again, and so on and so forth. I can also observe that I'm commonly dispatching to a certain method. So if I have a hash table or a hash map, and all of my keys are strings, then I'm going to be calling string.hashcode from the hash table and hash map methods. And so whilst it's true, I could be going to any hashcode method, I could be going to the object hashcode or something like that, I can do profiling and know where the common target is. So I can realize it's always string hashcode, and then I can inline string hashcode. But I can put some guard in there which says, if it proves to be anything otherwise, I can either deoptimize or I can go and do a regular method dispatch to it. There's an optimization which gets used, which is inline caching. You don't have to do it. Inline caching is where you remember the last target that a method dispatch went to, and you assume that because you went to it last time, you're going to go to it again. But it's kind of unnecessary if you've got decent profile data. So Java has a lot of stuff. A lot of this stuff existed before. And some people said that class loading is kind of the big new thing that Java introduced that no one had ever seen before. This ability to kind of dynamically take class files from the internet and include them into your program, or take them from anywhere a class loader can go and grab them. However, how can the JVM make optimistic assumptions about, this interface only has a single implementing class? And what can my method inlining, if I've inlined a method, how do I know that someone's not going to later on override that method and invalidate the inlining assumption there? So class loading throws up this challenge, and the solution to it is, to de-optimize, to say, oh, I got it wrong, de-optimize, and the de-optimization, in the worst case, will roll back and start using the interpreter again.
How does it determine whether it's done wrong?
So the class loader has to record. So the question was, for the benefit of the microphone. So the question was, how does it determine it's done it wrong? So you can either in the dynamically generated code, you can put guard tests in. So in the dynamically generated code, you can go, if this isn't a string, then de-optimize this method. Or you can record information in tables. So the class loader has a table associated with it called the dictionary. And in the dictionary, you can remember that this class has got, certain dependencies, like, that it's only got one interface. And if that, this class is a single implementer of an interface. And if anything loads which kind of invalidates those assumptions, then you can bring the VM to a safe point, and you can go and de-optimize all of that code. You can't just do it arbitrarily, because there'll be things running that code. But because the class loading happens at a particular point, then you can actually do it semantically correctly, and so on. If the VM is doing its job well, then it shouldn't be problematic, because the VM has what's known as an adaptive optimization system. And the adaptive optimization system is keeping track of the assumptions that the VM is making, and making cost-benefit analysis, and determining, what should it compile, with what compiler, what kind of assumptions should it bake into the generated code. And if the adaptive optimization system is working well, then the de-optimization will rarely happen. It will happen because you want to make these very optimistic assumptions, because when they hold, it's a really great performance win. Yeah, and this is really why Java can really beat C++ and C and so on. They have to be conservative. With the latest versions of GCC, you're getting into things like link time optimization and so on. But even in that scenario, they're looking at the whole program, and they have to conservatively assume that any code path which exists in the program is going to happen. Inside the VM, you can go, that's never been run. I'm just going to assume that if I ever get to that piece of code, I'm going to de-optimize the whole method, switch back to the interpreter. And it means you can make very small, fast bits of code with very aggressive assumptions in them. Level, what kind of problems do you see if de-optimization is occurring a lot? So for de-optimization to be occurring a lot, you've got to be compiling code, and then for that code to be being de-optimized. So one of the things you'd observe is that a lot of CPU time was being spent by the compiler threads of the VM. So if you've got exposure in your profile or whatever to the compiler threads, you can see that they're running a lot. There's also a command line flag called -XX: plus trace de-optimizations. And if you switch that flag on, you can see what de-optimization events are occurring inside the VM. If you start seeing a lot of them, then you know that the VM is doing something wrong. Now, the VM doesn't do things wrong, so you shouldn't get paranoid and think, oh, I've heard about this de-optimization stuff, the VM's going to make all of these aggressive assumptions, and it's not going to, so what the VM does is, if it sees one of its assumptions has been invalidated, then it adds it to its profile data. And when it comes back to recompile that code, it's going to recompile it in a different way and not make the same assumptions. And so you'll see a de-optimization event once, It's only when the compilers are broken, and I've seen compilers which are broken, but it's only when the compilers are broken and the adaptive optimization system is broken that you'll get repeated de-optimization things going on. Yes?
Can we force the compiler
To compile a piece of code? You can't. Well, not quite true. You can force the compiler always to run, and back in my example, for my Fibonacci example, I'd force the compiler to run by using a command line flag called xcomp, and that just says always use a compiler. You don't normally want to do that because it'll have a big performance overhead. You want the adaptive optimization system to be working and making these decisions for you in general. So what can you do to encourage the compiler to compile a particular method? Make it small and hot. Yeah, small hot methods, the VM loves them, and it's going to compile them. So if you're, if you have something like, if this condition holds, do something nice and fast. Otherwise, do this big complicated thing. Move the complicated thing into another method, and then you're going to make that method smaller and more attractive to the compiler to inline and to compile on its own, and so on. Because the adaptive optimization system is making these cost-benefit analysis, and part of that is based on the length of the method. Unfortunately, it's a crude heuristic, but it is what it is. The compiler doesn't spend energy compiling cold code. So if people are going to start going on about trace compilation or something, no. Sorry? So Java agents are used to enable debugging through an API called the JVM tools interface, and before that was the JVM profiling interface. And the question was, do these profilers affect de-optimization? And the answer is yes. What the JVMTI agents do, the Java agents as they get specified in the command line, what they do is they say, I'm an agent and I want these features from the VM. So they might say something like, I want to be able to single step through bytecode. And the JVM can go, that's a real nuisance to implement inside a compiler. Yeah. So what it can do in that situation is it can go, if you really want to do that, then use the interpreter. So if you switch on that JVMTI agent, if you use the JVMTI agent and it uses that option, then the VM can start becoming very conservative about what it's going to do and so on. And you can start seeing different behaviors in that you'll be spending more time running in the interpreter than running in compiler-generated code. Now, there's no reason why you can't single step through bytecode if it's compiler-generated code. It's kind of like, where does the JVM guy spend his energy? Does he spend his energy making profilers run very quickly for specific cases? Or does he spend it doing cool stuff like vectorization and escape analysis and all of these kind of good stuff for people who aren't running code with profilers and so on? So people have done a lot of stuff with the JVMTI interfaces and so on. Most JVMTI interfaces aren't fully implemented by most VMs, but yeah, it is what it is. So
back to the other question, are final static or private methods more likely to be optimized?
So the question is, are final static or private methods more likely to be optimized? The VM doesn't care. The JVM doesn't care whether they're private, static, final.
In terms of being dynamically dispatched? Couldn't be.
Yeah, if they're static or private, then you don't need dynamic dispatch. They're only ever going to go to one target. So static and private is a good way of kind of forcing the hand of the inliner, but you shouldn't need to. The profiler should be able to figure out the inlining itself and go, there's a single target to this stuff. So the key message is, write clean, nice, easy to debug, good quality code. Don't worry about what the JVM's doing. It's far smarter than you are, and it's there's people who should know better, like the Scala people. They do ridiculous things which completely break escape analysis, and it's frustrating. And then they tell you about, this is a really great optimization. You go, no. Okay, so that's kind of capturing that last comment. So the JVM's compiler and the adaptive optimization system and so on, they're going to do all of this smart stuff, and you shouldn't worry about it unless you want to. And then I've hopefully given you some pointers to some of the -XX options, and you can kind of get involved and look at the machine code that's being generated and so on. And it's all open source, so go and play around with it and do good stuff. And doesn't have, certainly in 2008 it was just an interpreter.
Right.
Trace compilation was my PhD thesis. Haha! But I won't bore you with the details. But trace compilation is a different way of looking at compilation, where instead of looking at hop methods, you look at hop basic blocks. And the problem with that is that if you start looking at things as basic blocks instead of methods, you lose the call stack. So if anything becomes uncommon, then you have to go and recreate the call stack. And if you look at what architectures do, hardware architectures, they do things like they predict that when you do a call, you're going to return to the next instruction after that call. So the problem with trace compilation is they have to kind of get around the fact that they've been so smart that they've kind of gone beyond what the architecture was actually expecting them to do. And so they have to be so smart that they're going to kind of win back that performance loss and so on. And kind of in the extreme, they're going to kind of equal each other in terms of performance.
So then to follow the question, do some of these
Have smart instructions which help JIT compilation. When they came up with all of these smart instructions, the one I'm most familiar with is that they have an explicit null check instruction, which is compare this value to 0 and trap if it is. And how does a regular JVM handle that? It makes sure that any of the pages of memory which are at address 0 and above aren't mapped in. And so if you ever try and load or store to those low pages of memory, then it's going to create a page fault, and it's going to create a segmentation violation. And then it goes and handles that and goes, oh look, it's really a null pointer exception violation. And so ARM have got these instructions, and I can't find a single use for them, because we've already kind of long engineered around the problems that these instructions were trying to solve. They might have come up with some other great ones, but I'm unaware of them. And my research group boss was the co-inventor of the ARM instruction set. So okay, so garbage collection. So memory safety is this really great stuff. We can allocate objects, and look, you can see the author of the slide deck was called Eva. So you can see here we're doing memory allocation, and I didn't need to worry about the fact that I've created some, I've used some resource, I've used some memory. I don't need to worry about trying to reclaim that memory. If I was working in C or C++, I'd have to try and free up that memory. Otherwise, eventually, I would run out of memory. Memory safety is the kind of the fact that the runtime system does this for you, and it's, thank God. So we've got garbage collection, and we've got all of this goodness. What do we want from a garbage collector? We want it to be parallel. We want it to use all of the CPU resources we have on our system. We want it to be concurrent. We want it to be generational. Fragmentation and compaction, the torture of tuning most JVMs. It's hard to work with this stuff. So these are getting away from my slides. So we're creating objects in memory. So we're saying these regions of memory are going to be used for this particular object. And the simplest way we can do that is just have a pointer and go, okay, we'll put an object here and we'll move the pointer up. And then the next object we allocate will immediately allocate above that pointer, and we'll bump it up again. Okay? At some point in the future, we want to work out what objects are alive and which objects are garbage. Now, one of the things with garbage collection is we don't want to spend time tracing through stuff which is garbage. We just want to work from a set of root nodes, and the root nodes tend to be things like static fields and values in registers and values on the stack. We start from those root nodes, and we want to find what can these root nodes find in terms of objects which are alive. And this is marking of the objects. There are other ways to do garbage collection. You can do reference counting and so on, but reference counting. Every time you use a field within an object, you have to bump a counter up and down. It sucks in terms of performance. So what you really want to do is you want to do tracing, and tracing only pays a penalty for objects which are alive. If we're doing tracing to find what objects are alive, anything that isn't alive is therefore garbage. And if we're not going to move objects around, then we need to do some kind of maintenance of these things. So we can start putting things onto free lists to remember, this memory is now available for us to reuse again. But that means we get away from doing our simple bump pointer allocation. We have to go and look at free lists and go, oh, there's something on the list which isn't currently in use, and I can go and use that. So that kind of garbage collection is called mark and sweep. So you go through and you mark everything that's alive, and everything else is kind of swept out of the way. Generational collection, I know there's a slide coming up on generational collection, but the observation is that most objects die young. So it's the so there are different forms of the generational hypothesis. There's a weak one and there's a strong one. The strong one says that the older an object gets, the probability it's going to die kind of increases in proportion. That doesn't tend to hold. But the weak generational hypothesis that the vast majority of objects which get created will then just die, it does hold. And this is an interesting observation because it means that we can focus our garbage collection energy onto a small set of freshly allocated objects, and not look at every object in the entire system. We can just look at the the recently allocated ones and concentrate on trying to reclaim the memory that they were using if they're dead. So come through to the generational stuff. Fragmentation and compaction. Did people remember what it was like to defragment hard drives? Yeah. So you're familiar with the term fragmentation. So fragmentation is that you've got things distributed around in memory, and what you'd like to do is kind of push them all together and make more efficient use of the memory. And if you don't do this, at some point you're going to there's going to be so much wasted space in your memory that you're going to run out of it much faster than you normally would. So this leads to a thing where you want to do compaction, and when you do compaction you want to move objects around. And if you start moving objects around, that means they can be in two places in memory. And that's a problem, because if your application is running at the same time as the garbage collector, how can the object be in two places? Which object do you use? And so let's carry on working through the slides, because I think there's stuff coming up on these. So most of the stuff is, and we have the VM memory for the JVM, and that's very small, don't worry about it. Worry about what your application's using, which is this great big whopper over here. When we do allocation inside the hotspot VMs, I mean there's much simpler VMs out there which don't do this, then we're going to do thread local allocation. So what we want to do is, we've got this pointer that we're bumping up in the simplest case. The problem with that is that if multiple guys are trying to bump this pointer up, then we've got race conditions which can exist. If we make the pointer thread local, then that all goes away. Fantastic. So what we do is we have thread local allocation regions. So here we've got a thread A, which has a thread local allocation region. We have thread B, which has got a thread local allocation region, and we're placing objects into these T-labs, as they get called. And then thread B goes and comes along, and he's trying to put an object into his local allocation buffer, and there's no space for it. So this is the most common cause of kind of a GC event having to happen, is that you've filled some finite memory resource. Okay, so in the regular kind of hotspot VM, what we have to do at this point is we're going to go, okay, we need to do a GC cycle. We need to work out what's alive. We need to, throw away the garbage. We want to do compaction, possibly want to do compaction. You normally don't want to always do compaction, but you're always going to sometimes need to do some compaction. And so what this means is, because you're moving things around, the application can't deal with things being in multiple places at the same time. So the best thing you can do is stop the whole application and do your garbage collection. And this is what leads to GC pauses. Okay. So here we are doing some garbage collection. I hadn't seen the animation. That's new to me. Okay. So for concurrent garbage collection, we want the application and the garbage collection to happen together. And this slide deck refers to the Azul garbage collector as the generational. So we've got old and young generation. We've got this efficiency where we realize that we don't always want to be scanning the old generation. Pauseless, in that it's never going to have these safe point pauses. Garbage collector. In new terminology, we've rebranded it, the C4 garbage collector, which is the continuous concurrent or concurrent continuous compacting collector. So Gil thinks of these things. It's C4, which apparently is an explosive. And so what we want to do is we want to be able to move things around. What's this slide deck showing me? There's not enough room. Okay, generational collection. Fine. Promotion. Oh, we don't care. Promotion is just when something is young and then you go, haha, now it's been alive for a certain amount of time, I want to promote it into the old generation. Okay. And then compaction. So that hasn't mentioned how you actually do any of this smart stuff. So what's the problem? We've got objects in two places. How can we deal with the object being in two places? What we need is some smarts which tells us, where is the object in memory that we're interested in. And normally the object we're interested in memory is going to be in one place. It's only when some compaction is going on that it's going to be moved to another place. So what we need is something which says when we have a pointer to something which is being relocated, make sure it points to the thing which is being relocated. And so this is a read barrier. And this is kind of the big difference between the Zing virtual machine and the hotspot virtual machine is that the Zing virtual machine, the Azul one, has read barriers. And this property of having a read barrier avoids garbage collection pauses. And so, great. There are some subtleties to that. You can try and reduce the garbage collection pauses via other means. And certainly Sun tries to do that, but they don't do as good a job. And this is kind of an example of a production concurrent mark sweep, which is the concurrent garbage collector that Sun have. And here's what the command line should be if you want to kind of tune the garbage collection. And normally what these people are trying to do by tuning the garbage collection is trying to make sure that everything ends up in the nursery, in the young generation, and that they seldom get promoted into the old generation. Because if they end up in the old generation, then you're going to have to look at the whole of the heap to actually work out what data is alive. And there are various kind of white papers on how you can do garbage collection ergonomics, as it gets called, to try and get these things to work. I mean, basically the take home is this is a mess. Get yourself a proper garbage collector and buy some Azul software. And the other thing with this is that these garbage collection pauses only get worse as your heap sizes increase. So it's realistic to think that a current JVM is going to start getting unacceptable garbage collection pauses. A pause which is going to mean that you miss a heartbeat and you end up rebooting a server because it's trying to compact. It's trying to visit the whole of 4 gigabytes of heap, which just when you try and do that in a garbage collection pause takes many seconds, and that means that you can end up missing a heartbeat. If you miss a heartbeat in a kind of a server environment, then it looks like the server has died or crashed or something, so you end up rebooting it. It wasn't that at all. It was just that your garbage collector kicked in. So this is a real problem, and that's why Azul has a real solution. Okay. So these come from Eva. Oh, don't be afraid of garbage, it is good. Don't like finalizers. Finalizers are just a mess, because what they're trying to do is they're trying to recoup resources, typically from the operating system or something, and there's not much control over when they get run. In Java 7, you're getting things like auto-closable and things like that, so the need for finalizers is going to be reduced. The way they're implemented in the VM is kind of messy as well, so I wouldn't be too afraid of them, but know their limitations. Always be careful around locking. Well, if you're writing very parallel things and you have a lock and everything gets serialized on the lock, guess what? That's bad. So make things concurrent when you can. Benchmarks are often focused on throughput but miss out on real GC impact. So it's very common for people to game benchmarks. And one of the ways they can game benchmarks is they can set up the garbage collector so it doesn't do an old generation garbage collection pause whilst the benchmark is running. So typically a benchmark will kind of run several iterations. If you do your old generation pauses in between the iterations, then it never gets timed. And that gives you very nice garbage collection, very good performance numbers. And so guess what? When people are when performance engineers are trying to generate benchmark numbers, this is what they'll try and do because it makes their VM look faster than it actually is. If you're an application guy and you actually care about getting these pauses, you should kind of wake up and benchmark yourself. Okay, so I'm at the end. Hopefully I haven't used the whole of an hour and 45 minutes. JVM is a great abstraction. Hopefully you've kind of seen into what the JVM is doing in terms of the compilers. I've talked some about the garbage collector. The garbage collector is a much more complicated beast than kind of the few slides which were in the Let's On. But kind of the take home is that you need to do something smarter with the garbage collector than has typically happened. Compaction is kind of this nasty with we like memory safety, we don't like garbage collection pauses. Why do we get garbage collection pauses? Because of compaction. How can we avoid these pauses? We can be continuously compacting, avoiding the situation where these compact pauses are going to happen, and Zing is kind of at the front of doing this. What is Zing? Okay. Read the slides to you. I already said generational pauseless garbage collector is now known as the C4 garbage collector. It's the garbage collector inside the Azul software, JVM that we produce. Originally, why did we develop this whole platform? We had these server boxes. Sasha mentioned earlier on that the first one we were showing off the boxes. So these systems have got 864 processor cores in them, and I think 640 gigabytes of RAM. So they're big. It's a lot of memory, a lot of RAM, a lot of CPU cores. And when you're at if you've got a JVM at that kind of size, then you can't, guess what, 640 gigabytes, if you're going to do a GC pause, that's going to take a while. So you have to engineer around it. And you want to engineer everything to be as concurrent as possible, and so on. And so, Azul has been focused on this problem for 8+ years. It's really great that, in terms of the number of cores that you're getting now inside a laptop, inside a desktop, inside of your common server, Intel are catching up with what Azul has had for the last few years. But that's kind of some history. Okay, Q&A.
So, can you elaborate on how you work? What are the properties? What are you exploiting that others are not doing?
So the real answer is that there's a read barrier there. Right. So the read barrier means that when you load a reference from an object, so you've got a field which is a reference. So maybe it's a linked list, it's the next field, so it's the next node in a linked list. You're loading that reference out of an object into a register, say, and immediately following that you do this read barrier optimization. This read barrier operation. On the original Vega hardware, this was a single instruction, and rather than it being called read barrier, it was called the loaded value barrier. On x86, we have something equivalent, and it's super smart and it's super fast and it's about the same cost as the LVB instruction on the Vega hardware. What does the property of the LVB give you? It gives you this property that whilst an object can be in one of two places, you only ever see it in the final place. And so if it's not already in that final place, you actually do the copying. The application thread will actually do the copying itself. However, that's bounded so that it only ever has to do a small amount of copying. If it's a large amount of copying, it does a small amount of copying and then asks the garbage collector to help it out and do everything else. And
the race condition of the concurrent
threads and garbage collection threads, you have to do compare and swap operations so that, you know, if the garbage collector is relocating something and the mutator is relocating it, the winner of the compare and swap is the guy who actually wins the, you know, now it's been relocated, and then, you know, the application continues with whoever was the winner of the compare and swap operation. And there are you know, the chance that that happens is very rare because copying is a very unusual operation. The normal situation is that you've just got a pointer which is pointing at the old location, you just need to move it to the new location. So copying is unusual. So Gil can give much more detailed explanation of all of these things because you might have guessed, I tend to work more in the compilers rather than the garbage collector, and so yeah. Of the JVM optimizations, and I specifically mentioned escape analysis, and the Scala guys in Switzerland did a nice paper on this and submitted it into a workshop that I was the chair of, so I knew the paper quite well. And what they were actually doing was, because invoke dynamic doesn't exist, invoke dynamic is this new bytecode which is going to kind of help languages like Scala and so on, they were using reflection for doing method dispatch. And what they were doing was they were going, let's remember the method object for doing the method dispatch. And so they were storing this method object into a static final or a final field or whatever, and going, now I remember what the method is, I can just reuse it, I don't need to recompute the method object all the time. However, because they've taken this method object and they've written it into a field, it's now escaped. So the escape analysis can't kick in, because it has escaped, it truly has. What the escape analysis will do for reflection is so behind the scenes of reflection, the runtime system will generate bytecodes, and the bytecodes will do the reflective method call for you. And if you avoid the escape analysis optimization, then you can't realize that the method object, whilst it's created, it has no purpose other than to carry around these bytecodes. And all these bytecodes are doing is doing a virtual method call. So what happens in this particular case for Scala, and hopefully they've fixed it, or Hotspotter has actually got its escape analysis working slightly differently or something, is that because they store the method object, they break the escape analysis, and then you don't get the direct virtual method calls through to the target. So you can do reflective method calls, and it's the same performance as just a regular method call if you can inline everything and escape analyze it and so on. And I've got research papers on it, so. But the JVM, so Hotspot and JVM and pick your virtual machine, they tend not to have something which is like, if people are familiar with the C function alloc A, which is kind of like allocate on the stack, they tend not to have that operation inside the VM. So, but they do put objects onto the stack. How do they do that? Well, what they do is they do the escape analysis, realize that the object doesn't escape, and then they turn it in the next field from our iterator becomes one of our registers in our infinite pool of registers. And then when we register allocate that, it'll either end up going in a register, but if we're limited in terms of the number of registers we have, then we'll end up spilling it out onto the stack, and then when we need it again, we fill it back in again. And so this is effectively stack allocation, but not quite. Kind of a side note is that the Vega architecture actually did have a notion of stack allocation and so on, but not to worry about that. Make it very large. make it large, make it cold, you know, all of these things. Basically, the JVM is going to inline it if it thinks there's a performance advantage to inline it. You know, an accessor method should always get inlined. So don't, you know, if you're trying to avoid inlining an accessor method, you know, bad luck. There's a command line flag -XX minus inline, which switches off all inlining in the VM. If you were, you know, crazy enough to want to defeat the whole of the compiler.
How do you test correctness of
The concurrent things, and it sounds like they're going to have lots of bugs in them and so on. And how do you avoid this? So you invest in QA. That's a big way to solve these problems. But you can also recognize things that there are certain invariants about the code, about the heap, and you can make sure that those invariants hold, and then you can have kind of slower debug versions of the VM which are making sure that all of the invariants are always holding and that your heap is always in the correct state and all of these kind of things. And then when they don't hold, you can go, oh, we need to go and fix a bug. But you know, if we've done our job right, this doesn't affect you, and so on. But yeah, it's a lot of work. It's complicated, you know. Yeah, I've got a job. That's great. You know.
So is it good or bad for JVM to have too much
of reflection? So people have told me in the past, you know, avoid reflection because it's got this huge performance overhead, and I usually say to them, show me the numbers, and then, you know, they never come back to me. And the reason they never come back to me is they've gone and looked at the numbers, and when they actually have some hot code which is doing reflection, it works very well. So it's true in very early JVMs there was very little optimization there. So a method dispatch via the reflective mechanisms would be kind of like hundreds of instructions, whereas a regular method dispatch would be, say, one instruction. These days, you know, I think the kind of the rule of thumb they have is that it's kind of twice as costly as a regular method dispatch. The problem with this is that you need to realize it's a dynamic system, and so it's when it gets hot you're going to see these performance wins and so on. In the virtual machine, you know, the metacircular VM I did a lot of work on, the cost of a reflective call was exactly the same as a regular method call. We optimized everything away. And so on. So there's really no reason for it. The problem is to get that optimized version, you've got to get the optimizing compiler in there. You've got to, the adaptive optimization system has got to kind of like realize, oh, this does nothing, and zip and remove all of the code which was, you know, causing the performance overhead. Yeah.
What's the difference between a metacircular VM and a regular?
The idea behind metacircularity is that you should eat your own dog food. So if you read kind of like the Dragon book and things like that, there's kind of a rule of thumb that when you write a compiler, you should write it in the language that you're actually trying to compile. And clearly there's a bootstrapping problem when you do that. So if you look at a regular VM like Hotspot, it's written in C++. So it's not written in Java. And so this eat your own dog food property doesn't exist. A metacircular VM eats its own dog food. So JAGSR VM is an example of a metacircular VM, which is a VM written in Java. It sounds like that shouldn't be possible. It's very possible. People have built whole operating systems entirely out of Java, and so on. There's no reason why not. And the advantage of the eat your own dog food is when you realize something is an issue, you go and fix it in the language, you go and fix it inside the VM, and you kind of get this beneficial circle happening. You know, whilst it's, you know, it's kind of unfair to say that Hotspot is kind of not eating its own dog food. It did have the bootstrapping problem. You know, what other VM was there for it to bootstrap itself on? What happens inside Hotspot is, you know, things get pushed out into the Java code so that they can take advantage of all of these optimizing compiler goodnesses and so on. Yeah. You have application threads and you have garbage collection threads, and you've got your heap, which has got, you know, things which are alive and things which are dead, and you need to It's possible via an algorithm we have, which is this continuously compacting concurrent collection algorithm, and there's a whole research paper which describes it. So I'm trying to think, is there a quick way to kind of summarize that for you? It's complicated, but essentially you make sure that when you're doing this, this compaction and so on, you're not reliant on things like locks and so on. And I already said, if the application can't make progress because it's waiting for the GC to do something, the application actually makes the progress itself, a small amount of bounded progress, and so on. So the big thing for Java 7 really is just this invoke dynamic bytecode, and the invoke dynamic bytecode has these interesting method dispatch properties, but it's being kind of created with a kind of a knowledge of how the VM is actually working. So is it really a VM optimization? It's kind of the VM guys holding hands with the guys who are generating the bytecode and realizing there's kind of a more efficient way to do something. And invoke dynamic also exposes kind of some clever call site semantics and things like that. Really, what you should be waiting for is just the optimizations would already exist to get better. So, the new Intel processors have got AVX instructions. So AVX instructions have got 256-bit registers, and they're also 3 address, and there's all of these other things which are very un-Intel, and so on. And so, Hotspot has to add support for these instructions. And when you're doing vector optimizations, you've got to do vectorization. So that's realizing you've got a certain loop structure, and that you can actually do kind of 4 operations instead of 1 inside that loop structure. Other things, escape analysis needs to get better. Everything needs to get better, but it's kind of more of the same. There's been some interesting research on things like object inlining and different things like that. It's a very dynamic and interesting research space. How does Groovy do on the JVM? Compile some code. How are we going to know where the incoming arguments are for the method? So in the Zing virtual machine, we pass arguments through registers. This avoids us having to load them from the stack. They're just there in the register. And this is common on 64-bit x86 code. On 32-bit x86 code, it's very common to pass things on the stack. The number of parameter registers that you have to pass things in registers is only 6. So if you have more than 6 parameters, then the extra parameters are going to get passed on the stack. But of course, when these things get inlined, all of this passing on stacks and passing in registers all goes away because, the inlined method becomes part of the graph, and these things never kind of end up in registers. So, to kind of answer your question more directly, it's kind of a choice for the VM as to what is the calling convention it's going to use, and it just happens for the Zing VM we use pass by register for efficiency reasons.
Do you have any benchmarks that show the performance differences of non-trivial? That has been very insightful. I really appreciate it. So, as you guys probably know,